We've been to the moon before. So going back, it should be easier, right? I mean, we've already got the blueprint. Well, it's not quite that simple. Actually, it's not simple at all. The new Artemis missions are so fundamentally different from Apollo, it's kind of like comparing a single cannon shot to a full-blown naval invasion. So let's break down this invasion, piece by piece, and really dig into why going back to the moon is so much harder than you might think. Apollo, it was elegant, almost brutally simple. You had one massive rocket, one direct shot to the moon. That was the whole deal. But Artemis? It's a completely different beast. We're talking about a distributed campaign. It's this incredibly complex, multi-launch, multi-vehicle mission that has to rely on a whole fleet of spacecraft working together in this perfectly synchronized ballet. And the first and maybe the biggest new challenge happens way before any astronaut even thinks about putting on their suit. It all starts with this unprecedented logistics dance that has to play out absolutely perfectly in low Earth orbit. Okay, get this. For the entire Apollo program, how many times do you think they had to refuel in orbit? The answer is 0. Not once. The mighty Saturn V rocket just carried everything it needed, all in one single colossal launch. All right, now let's flip over to Artemis III. The lander for this mission, it launches empty. And to fill that thing up, you need a whole fleet of tanker rockets. We're talking 15, maybe more, separate launches and dockings, and that's all just to get the lander gassed up and ready for its own trip to the moon. So let's walk through this, because it's pretty wild. First, they launch a fuel depot, basically a gas station in orbit. Then, a whole fleet of tanker rockets, 10, 20 of them, launch one by one to go fill up that gas station. Then, the actual lander launches, docks with the depot, and fills its own tanks. And only then, after all that, can it finally head off to the moon to wait for the crew. And here's the kicker. We have never, ever done orbital refueling with cryogenic fuels on this scale. We're talking about super chilled liquids that are constantly trying to boil off into space. If just one of those launches, one of those dockings fails, the whole mission is a scrub. The whole thing. Okay, so let's say that incredibly complex dance works perfectly. The crew finally gets to launch. But here's the thing. Even where they go to meet their lander is a whole different ballgame, and it's way, way more challenging than anything Apollo ever had to deal with. So Apollo's orbit was, pretty straightforward. They were in what's called a low lunar orbit, or LLO, just buzzing along about 60 miles above the surface. It took them 2 hours to do a lap, so if you missed your docking window, no big deal. You just wait for the next pass. But Artemis, oh man, it's using this crazy thing called a near rectilinear halo orbit, or NRHO. And the numbers here are just staggering. Instead of a nice circle, it's this huge, stretched out loop that swings from 1,000 miles out all the way to 43,000 miles away. One loop doesn't take 2 hours. It takes 6.5 days. So what does that actually mean? It means there are no quick second chances. None. When the crew arrives in that Orion capsule, they get one shot, one window to meet up with their lander. If they miss it, they're not looping around in a couple of hours. No, they might have to wait an entire week, all while burning through their precious life support. The stakes for this one maneuver are just astronomically higher. All right, so they've pulled off this insane rendezvous. Now they've got to land. And this is where the sheer mind-boggling scale of the new hardware creates a whole new category of problems. Because we're not landing a little lunar module anymore. We are, quite literally, landing a skyscraper on the moon. You remember the Apollo lunar module, the Eagle? It was about 15,000 kilograms. Neil Armstrong? You know the story. He famously had to take over and fly it manually to dodge a field of boulders. Well, the Starship lander, it's almost 100 times more massive. It is so big, so complex, that the crew can't fly it. It has to land itself, fully autonomously. And getting out? Oh, it's not a simple little ladder anymore.
Picture this. When this absolute behemoth finally touches down on the moon, the crew cabin, their front door, their only way in or out, is going to be about 100 feet, 10 stories up in the air. So how do they get down to the surface? They have to take an elevator. Yeah, an elevator. And that brings up a question the Apollo astronauts never had to worry about. What happens if the elevator breaks? I mean, really, what's the backup plan? If that thing gets stuck, they are literally stranded 10 stories up on the moon. It is a brand new, absolutely critical point of failure that just didn't exist before.
Okay, let's say the elevator works, they get down to the surface safe and sound. The challenges are far from over, because where they're landing is a totally different place, a much more hostile, much more alien environment than anything Apollo ever faced. We're talking about the lunar South Pole.
So, when you think about the Apollo landings, you picture that bright, dusty landscape, sun high in the sky. That's because they landed near the equator. But at the South Pole, the sun just scrapes along the horizon. And that creates these long, permanent shadows that are just pitch black. I mean, so dark that an astronaut literally can't see their own feet without powerful lights on their suit. And inside these cold traps, that lunar dust, the regolith, could be mixed with water ice. We have no idea what that does to the soil. Is it going to be firm? Is it going to be slushy? Is it stable enough to hold up a 1.3 million kilogram skyscraper? That's a huge unknown, and we won't get an answer until they're actually coming in for landing.
And they're going to be exposed to all of these new dangers for way, way longer. On Apollo 11, they did one spacewalk. It was about 2.5 hours. For Artemis III, the plan is for multiple EVAs, totaling more than 24 hours on the surface. That's a tenfold increase in the amount of time they're out there dealing with all these new risks.
So, finally, after navigating this insane orbital belay, the high-stakes rendezvous, landing a skyscraper in a pitch-black, unknown territory, they have to get home. And of course, even the return trip involves a maneuver that is more complex and demands more precision than anything Apollo ever tried. It's called a skip entry. Basically, the Orion capsule is going to slam into the atmosphere at 25,000 miles an hour. But instead of just barreling straight through, it's designed to use its own lift to actually bounce off the top of the atmosphere, skipping back out into space for a moment like a stone on a pond. This gives it a crucial moment to shed a massive amount of heat before it dives in for a second time for the final descent and splashdown. And the precision needed to pull this off is, well, it's terrifying. It is a genuine life-or-death calculation. If that entry angle is too shallow, by even a tiny fraction, they just skip off the atmosphere and are lost in deep space forever. If it's too steep, they burn up. There is no margin for error.
So let's just recap for a second. You've got this insane orbital logistics puzzle. Then you layer on a dangerous, unforgiving lunar orbit. Then you have to land a brand new skyscraper-sized vehicle in a totally hostile and unknown environment. And you cap it all off with a razor's edge return trip. So, what's the cumulative effect of all these new challenges, all this new risk?
Well, let's just lay it out. With Apollo, a launch failure meant one rocket failing. With Artemis, a launch failure could be any one of those 15-plus rockets failing. Apollo had one critical docking, Artemis has a whole chain of them. For an Apollo astronaut on the moon, the biggest danger was, tripping over a rock? For Artemis, it's getting trapped in a freezing cold shadow or having your elevator break 100 feet in the air. The point is, at every single phase of the mission, the number of ways things can go catastrophically, mission-endingly wrong it's multiplied. So, you see, going back to the moon isn't about retracing old steps. It's not Apollo 2.0. It's an entirely new, far more ambitious, and just vastly more complex undertaking. And that leads us to the final, biggest question of all. With the risk multiplied at every single step of this incredible journey, what's the reward? What are we trying to achieve that makes facing all of these new challenges worth it?